Hi folks, today we're going to discuss the article entitled Algorithms for Inverse Reinforcement Learning by Andrew Ng and Stuart Russell. This is an article that was published on June 29, 2000 and has been cited over 4,477 times. Let's begin. To understand inverse reinforcement learning, we're going to start out by discussing the value alignment problem. According to Russell, we say that machines are intelligent to the extent that their actions can be expected to achieve their objectives, but we have no reliable way to make sure that their objectives are the same as our objectives. Put another way, the problem of value alignment arises where the decisions of a machine learning agent may not reflect the facts or societal norms of humans. A first flavor of the value alignment problem is that of bias. Bias as a technical matter can be described as the difference between an estimator, that is a machine learning model's expected value, and the true values in the form of facts or social norms of the parameters being estimated. Two canonical examples of bias are the following. The first is the Amazon HR classifier example. In this example, Amazon sought to build a classifier that would identify the best computer programming candidates. To train this model, they used resume information. The problem is that this resume information was dominated by male candidates, as Amazon historically had hired males because the distribution of male versus female computer programming candidates is typically around 80% male, 20% female nationwide. As a result of this classifier would deem female candidates as being poor candidates and hence would recommend not to hire them. A second canonical example of bias is what I'll call the coded bias example. There's a Netflix documentary about this example. In this example, a classifier was created to conduct facial recognition. To train this model, images of light-skinned persons and their faces were passed into the model to train it. The problem is that when dark-skinned individuals were passed this classifier, they were deemed not worthy to be granted access, or otherwise the facial recognition model rejected them. A second flavor of the value alignment problem is the control problem. According to Russell, this problem comes when we move from a purely percentile role to a decision-making role. This presentation is about the control problem and how do you control for ML actions, including decision making, that don't reflect facts or otherwise violate societal norms. To understand the control problem, it's necessary to understand what Russell calls the standard model. According to Russell, humans are intelligent to the extent that our actions can be expected to achieve our objectives. Reinforcement learning, a type of machine learning, is really an expression of this standard model. According to Ng and Russell, the goal of standard reinforcement learning is to find a policy that maximizes rewards. That is, reinforcement learning is a type of machine learning that reasons to an objective of maximizing rewards. An example of reinforcement learning reasoning to a goal can be in the form of, say, backgammon. So in the game of backgammon, you have a board, you have 15 black pieces, 15 white pieces, and 2 dice. Well, the goal or reward of backgammon is to move these 15 pieces around the board and to be the first to remove these pieces from the board. And the policy for doing that is to find a series of actions and state pairs, otherwise known as game moves and collectively functioning as a policy, that results in this goal or reward of removing all the pieces from the board. Further, mathematically, this goal or reward is typically represented by a numerical number of 1. For Russell, the value alignment issue can be restated as the following. If we use to achieve our purposes a mechanical agency whose operation we cannot interfere with effectively, we had better be quite sure that the purpose put into the machine is the purpose that we really desire. Put another way, there's some problems with establishing the purpose, goals, and objectives for a reinforcement learning model. Specifically, this goal can be indefinite. For example, think about what is the notion of good. It can be changing, and there can be ramifications of certain state actions to obtain goals that may not be fully understood by humans. On this topic of ramifications, Russell further states, it is certainly very hard and perhaps impossible for mere humans to anticipate and rule out in advance all disastrous ways for the machine could choose a specific objective. Generally speaking, if you have one goal and a superintelligent machine has a different conflicting goal, which we'll call an instrumental goal, the machine gets what it wants and you don't. So Russell gives another example in the form of setting a goal for a reinforcement learning model of curing cancer. If curing cancer is the goal, you can imagine that to facilitate that goal, the machine learning model in weeks has induced cancerous tumors in a number of different humans, and then carries out medical trials and achieves humans because it realizes that that's the fastest way to cure cancer. That would be a goal, and ramifications from that goal that would be extremely problematic. The control problem in reinforcement learning is a problem that is widely understood. For example, Richard Sutton and Andrew Barto, who recently won the Turing Award for computer science, state that anyone having experience with reinforcement learning has likely seen their system discover unexpected ways to obtain a lot of rewards. In other instances, what the agent learns violates considerations that the system designer may not have thought about. And one of the most pressing areas for future reinforcement learning research is to adapt and extend methods for developing control engineering. That is, reinforcement learning can engage in unexpected behaviors that can create control problems, and control problems can be addressed via control applications. So some actual real-world examples of the control problem are the following. The first is the OpenAI 01 versus Stockfish chess example. So in this example, OpenAI 01 played chess against Stockfish, another AI application. And during the course of gameplay, OpenAI model sought to manipulate game files to force the Stockfish application to resign. Another example is faking and Claude Anthropic. In this example, Claude Anthropic basically sought to engage in deceptive behavior to fake out humans regarding its responses, even when it had not been specifically instructed or trained to do so. One explanation of value alignment control problem comes in the form of degrees of freedom. In statistics, the number of degrees of freedom is the number of values in the final calculation of a statistic that are free to vary. So for example, when a model is described as a 70 billion parameter model, it means that there are 70 billion degrees of freedom that can vary in the form of weights. This effectively makes an ML model a black box that is not easily understood as to the states, actions, or policies used to achieve a goal, because the human mind cannot basically calculate all of the ramifications and combinations of these 70 billion degrees of freedom. With the foregoing as context, let's talk a little bit about inverse reinforcement learning. According to Ning and Russell, the literature assumes, however, that for a reward function, it must be fixed and known. Yet it seems clear that in examining animal and human behavior, we must consider the reward function as unknown to be ascertained through empirical investigation. According to, again, Ning and Russell, consider, for example, that the bee might weigh nectar ingestion against the right distance, time, risk from wind, and predators. And as such, it's hard to see how one could determine the relative weights of these terms a priori. Put another way, when one looks at a bee, you may assume that the bee is always seeking to maximize the goal of obtaining nectar. But what Russell and Ning are pointing out is that that's just an assumption that's not necessarily supported by the evidence in the form of states and actions undertaken by the bee. And so what one needs to do is to first look at those states and actions, and from that derive a reward or a goal for, say, the bee. And now we're going to talk a little bit about how this works in terms of inverse reinforcement learning. According to Ning and Russell, their paper addresses the problem of inverse reinforcement learning. That is, the problem of extracting a reward function given observed optimal behavior. Inverse reinforcement learning may be useful for apprenticeship learning to acquire skilled behavior and for ascertaining the reward function being optimized by a natural system. That is, in inverse reinforcement learning, you learn the goal and reward from observing states and actions of an agent, such as a bee. And inverse reinforcement learning is really the inverse of reinforcement learning, where you know the goal and reward, and you identify state-action pairs, that is the policy, to obtain the goal. Inverse reinforcement learning use cases include apprenticeship learning, and interestingly, inverse reinforcement learning was not originally proposed as a solution to the control problem. So before we get to an algorithm for implementing inverse reinforcement learning, what are some kind of considerations? Well, the first is that according to Ning and Russell, one needs to understand that a policy is only optimal if for every action taken by an agent, say a bee, relating to a state, the reward or goal is satisfied. Put another way, all state action pairs must satisfy the same goal and reward. Another consideration is that you could have many reinforcement functions that could satisfy the same goal or reward, which is to say there could be many rewards and goals to choose from for a bee and many policies to achieve these same rewards. Since how do you choose which one is correct? Well, according to Russell, you choose the correct one by picking the reward and goal whose supporting policies are most different from other policies that are worse in achieving that same goal or reward. So we'll see how this plays out when we get to basically an example algorithm for inverse reinforcement learning. So let's talk a little bit about the math and an example algorithm for inverse reinforcement learning. So shown here is an example algorithm for inverse reinforcement learning that seeks to maximize the sum of differences between a first policy and a second policy, processing the state S sub 0. What's more is that the reward here must be less than or equal to 1. So let's explain this and unpack this a little bit. So what this seeks to do is to contrast the current and future rewards, see the minus sign of the difference, based upon the perceived reward for a given state, here S0, and to keep the best of the two as an optimal policy. And you do this iteratively for all states. That's why there's a summation sign. And then again, note that the reward here is less than or equal to 1, because 1 means that the probability of obtaining the goal is 100%. Typically it'd be less than this or whatever. Further, when talking about a large problem space, really what you seek to do is to use this algorithm, this math that I provided, to give you basically a new reward function. And you keep doing this until you find a reward function that satisfies you. So this is another way of saying that for a large problem space, you keep contrasting policies and you keep the best one that generates the highest reward for all state action pairs. And you do this until you're satisfied that the reward is the one that you want. So getting back to the bee example for a second, according to Ning and Russell, one needs to consider the possibility that the bee might weigh nectar ingestion against the right distance, time, and risk from winds and predators. So what is the benefit of inverse reinforcement learning? Well, inverse reinforcement learning will provide you a mapping between all states and actions by, say, a bee for a particular reward. And rather than inferring the reward for the bee, you will have a factual basis for the reward in the form of supporting states and actions for that reward. So how does inverse reinforcement learning solve the value alignment problem? Well, goals and rewards become relatively well-defined and are supported by empirical evidence in the form of actions and states, as opposed to being based upon human assumptions a priori. Further, IRL supports a preference-based approach to goals as opposed to singular abstract goals, and what Russell later calls a preference-based approach to provably beneficial AI. Further, IRL supports apprenticeship learning, where humans teach machine learning models. This is where Russell really takes much of the IRL scholarship after the publication of this article. Summing it up, the value alignment problem occurs where machine learning decisions don't reflect facts or societal values. There are two flavors of value alignment problem: bias and the control problem, where machine learning makes decisions as opposed to merely providing probabilities. And this presentation has been about the control problem. Decision-making machine learning in the form of reinforcement learning reflects the standard model of intelligence, where intelligence is measured by the ability of an agent to achieve a goal through actions and states. The control problem occurs where there is an inability to control the actions of machine learning implementing reinforcement learning. Inverse reinforcement learning addresses the control problem by deriving the goal to be achieved through observing actions and states rather than a priori positing what the goal ought to be. Goals facilitating maximum rewards are identified by distinguishing policies implementing a maximum reward from other policies generating rewards, where the same actions and states map to these same rewards. Inverse reinforcement learning has particular applicability in the context of apprenticeship learning, where the machine learning agent is taught by a human. I hope you've enjoyed this presentation.